All right, thank you for the introduction, Samir. And my name is Dmitry Liakh, and I'm from the Oak Ridge National Lab, the lab which deployed the largest GPU-based supercomputer in the world. And so in this hands-on session, again, I think John did an excellent job describing the CUDA programming model. So it should be much easier for me now to try to do some hands-on exercise after that great lecture. In essence, I will be presenting synthetic CUDA C++ linear algebra exercise where our test goal is to develop a very simplistic linear algebra library, which would perform some basic linear algebra operations on NVIDIA GPU. And like our main kernel of interest here will be the famous matrix multiplication kernel, GEMM, general matrix multiplication. And so our goal will be, so we'll first go through the way I implemented this kernel with different optimizations, and we'll compare the performance with the state-of-the-art cuBLAS implementation in CUDA BLAS library. And then finally, at the end of the presentation, the goal for the participants will be to implement similar GPU kernels similar GPU kernels for the cases where one matrix is transposed. So this is the brief overview. So I'll proceed to my presentation, and we will test this on Blue Waters because Blue Waters has Cray XK 7 nodes, and those nodes, each node has NVIDIA Kepler GPU K20X. And we'll be using Blue Waters nodes to test and run our code there. Or otherwise, if you have access to any GPU machine, then you can go ahead and use that GPU machine if you want. It doesn't matter, it should run on any machine which has at least Kepler GPU. And so the first slide here provides the instructions, and we need to check that everyone can clone the repository. And first of all, to log into Blue Waters with your user ID that you had received before. And then you can clone the repository here. And for your convenience, in the project directory, 1 second, I'll just go there and update it. So everyone should have access to /project/training. Then BAYR, and you'll see there it has a CUDA tutorial folder. So if you go to that folder, I'll just make sure it's up to date. Okay, now this repository now is up to date. So what you can do now, you can go in the, so you can go in this /project/training/BAYR folder that everyone should have access to on Blue Waters. And you can create your own directory with your name, or just name it whatever you want. And then you can just do, for example, you can just do create directory user and some name, of course. And then you can go to user. And then what you can do, you can just do git clone. So just go to the full path projects, training, BAYR. CUDA tutorial, and you just essentially clone that Git repository that I have into your own directory, because you'll be modifying the code and you essentially will be working on your own fork of this repository. So once you do that, you clone now, And you should see now CUDA tutorial in your own directory. And I think yeah, we should collect questions if someone has troubles performing these basic steps, because we need to make sure that everyone can clone it and make it and test it, so to confirm that it works. So the next step, so once you have cloned the CUDA tutorial repository, let me check the makefile. Okay, you will also need to copy the makefile from projects, I mean from the main CUDA tutorial directory, projects training BAYR CUDA tutorial. So this is my repository, and you can just copy the makefile into your cloned repository, because the makefile here is now tuned for Blue Waters. The default makefile is not tuned for Blue Waters, it's just generic, but this one is tuned for Blue Waters. And now you can just simply type make clean and make. Oh, I forgot. Okay, that didn't work. Oh, sorry, I forgot to update my modules. It's actually on the slide. So if you see there, the next step. So after you clone the CUDA tutorial Git repository into your own directory, you need also to set the right modules, and you need to do this module swap programming environment Cray to GNU, and swap GCC to one of the latest version 8.2.0, and load CUDA toolkit. And I'll just do it in real time. So please let us know if someone has problems cloning the repository. So we now do module swap programming environment Cray to GNU. We do module swap GCC 8.2.0. And we do module swap, module load CUDA toolkit. So now we can do make clean. So this instructions are on the first slide. And so you need to clone the repository, and you need to load the swap and load the correct Cray modules on the slide. And then you, inside your clone directory, you do make clean. And then you can do make. And so at the end, you should have the binary called blah_test, where blah stands for basic linear algebra. So this test is called blah. That's the name. So at this point, I will remind you that once you cloned the repository, the makefile is still not tuned for Blue Waters, so you need to additionally copy the makefile from the same repository into your cloned repository, and then you can proceed to making. So did you guys succeed? Everything's good? Cool. So here we all 100% success in Georgia Tech. I don't know what's going on in other centers, but if any questions, please let me know. And so the next step, obviously, is to run this test and make sure it works. However, this requires opening an interactive session, and I'm not sure if we have like now exclusive access. So you could open it. Okay, great. Did you run the test? Did it work? Okay. So did it say at the end that it like seemed like it works? Something like that. Okay. Awesome. Awesome. All right. Great. So. Do we have any Slack questions about this So I guess then everything works well so far, and I'll proceed to the next slide. So everyone now has the source, and we may need to inspect few files in the source. In general, this test called BLA library, basic linear algebra library, so it contains some higher level C++ interface to the main object in linear algebra called matrix. And we have a matrix.hpp header file which defines this class and defines some higher level operation, what you can do with matrices. Like, for example, you can construct a matrix by providing number of rows and number of columns. And then you can allocate. So when you construct a matrix, there is no storage associated with the matrix. Then if you want to provide the storage for the matrix, you can call allocate body method on the matrix, and then you can also provide the device ID. And device ID is just an integer, and -1 means CPU host, so your CPU. And if you want to allocate body on GPU, you provide the GPU number, for example, 0, because we have only one GPU. And so all this higher level interface is not our focus. This is just to make things running, and we only be focusing on the GPU kernels. But I need to explain first this interface, because you will look at the main CPP file where these methods, these functions are called. And so this allocate body method just provides the storage for the matrix. And you can decide either to allocate matrix body on the CPU or on GPU by providing the integer, a number, -1 or 0. And then you can call 0 body on the matrix, and 0 body essentially just sets every element of the matrix to 0. Then you can also call set body host, and this method will just set some random value to our matrix on host only. And then you can synchronize the value on multiple devices by just calling matrix.sync body. And what this does, you provide two integers. One is the source device, and the other one is device where I wanted to synchronize. And what it does, it just copies the matrix body from source device to the device you ask for. And again, this is all not the focus of this presentation. This is just to highlight what all this means in the main CPP file. So we have a class matrix, which is just higher level interface to the matrix object. Like our main concept in linear algebra is matrix, right? But we also want to define matrix operations. And for matrix operations, we only have 3. So in this kind of a learning exercise library, we can compute norm of the matrix on a selected device. So we can explicitly say which device we want to use to compute the norm. And in all our experiments, we'll be doing everything on GPU. So device always will be 0. So we can compute norm on the GPU device, and we can perform addition of 2 matrices on a GPU device, and we can perform a multiplication of 2 matrices on a GPU device. And inside the BLA library, these calls are then dispatched to specific GPU kernels, which implement either norm calculation or addition or matrix multiplication. And we'll be focusing on the kernels which implement matrix multiplication. And important thing to notice here is that matrix.multiply_add, this is the matrix multiplication call. And so this call requires obviously the A matrix, the B matrix, which are there. And so it multiplies them and accumulates the result into our main matrix that we are calling from. But also you have 2 first arguments which ask for optional transposition of the A matrix and B matrix. And by default, these arguments set to false, which means that we just take the A matrix and take the B matrix, multiply them, and accumulate the result in our result matrix. But in general, you can also say true to any of the arguments, and that means that we will be using the transposed matrix instead of the normal one. And so actually the exercise will be to implement GPU kernels, which actually realize this operations on GPU. So as of now, the main source file to open and look at is the main CPP. So the main CPP is the driver, and it contains a function called useBlah. And so in the main CPP, you have the main function, which does very simple things. It initializes the blah library, it tests it, then it calls useBlah, where all the work will be done, and then it shuts down the blah library. So we'll be looking only in the function useBlah. So the first function in the main CPP is the use_BLA. And so this function just implements our test. And in this function, you essentially will see these pieces here. So what this function does, so if you look at the source code, so if you open main.cpp and look at the useBlah function, all this function does is that it creates matrix A. I can actually open the source myself. So you can see that. So I assume everyone can see my source file screen, right? Yeah. Okay. So you can see that first of all, so in this function useBlah, the driver does the following. So it creates matrix A. So then it allocates the storage for matrix A on host. Then it sets matrix A to some non-trivial value on host, just any kind of random value. Then does the same for matrix B. And when creating when creating these matrices, you have a choice either to have underlying type float, so single precision, or double precision. So all the tests here use float. So we can safely now assume that everything done in single precision here. So we create matrix B, again allocate storage on host, set to some value on host. We create matrix C. We allocate storage on now GPU because we provide 0 here. So we allocate storage on GPU. Again, underneath all these operations perform CUDA malloc and CUDA memcopy and all those basic operations that you need, that John explained, that are used for creating storage on GPU and moving the data to and from GPU. So this is not our focus, so that's why we don't worry about these parts. Then we create matrix D on GPU. And then here we copy matrix A to GPU. Then we compute the norm of matrix A. Here, compute norm on GPU because 0 is here. Then we did the same. We copy matrix B to GPU, compute norm of matrix B on GPU. Then for our matrix multiplication case, we need to know the number of flops. And then we just compute the number of flops using the standard formula that we multiply all dimensions and times 2. And this gives the number of floating point operations in our given matrix multiplication. And then we proceed to our tests. So the first reference test is that we just perform this matrix multiplication using the kublas GEMM call. And so we repeat our experiment twice here. So repeat from 0 to 2. So what we do is just set matrix C to 0. Then we choose our GEMM algorithm. And 7 here is the kublas algorithm. Then we do the timing. And then we call C, multiply add. And this will perform matrix multiplication of matrix A times matrix B on GPU 0. And then false, false means both matrix A and matrix B are non-transposed. Yeah. That's not my editor, unfortunately, so I don't know how to do how do I do it in VI. Can you help me? So I don't use UI much. Yeah, but I think it would be nice to have like the line number, like on the left. All right, cool. So you see that in line. Oh, that's great. Thank you. So you see that in line 82. So from line 77 to line 90, we have we just run matrix multiplication using the CUBLAS library from CUDA toolkit, and then we call matrix C multiply add, and this multiplies matrix A times B on GPU 0, and both are non-transposed. So this is done at line 82. And this is a synchronous call, and it will just multiply two matrices, and it will return when it's done. And then we measure the time, and then we print how long it took, and what is the performance. So we divide flops, number of floating point operations, divide by time taken, and this gives us the flop per second performance of our kernel. And then for correctness, we also compute the norm of matrix C, and we also store matrix C in matrix D to later check the correctness if our own kernels give the correct result. So this is what's happening in line 76 to line 90. We just create the reference for our further experiments. Then proceeding further, the first algorithm for matrix multiplications implemented in BLA library is called brute force. So this algorithm has its kernel, which implements the matrix multiplication. And here in the main CPP, we just simply do all the same steps. But now, if you see in line 96, we reset our GEMM algorithm to 0. So now, instead of CUBLAS, the backend will be using our own kernel. And our own kernel, specifically the brute force implementation, which I will now go through soon. And then it does the same thing. So that performs matrix multiplication A times B. Both matrices are non-transposed, so false, false. And so this calls underneath the GPU kernel. It performs the matrix multiplication using our algorithm. And then we see how bad our performance is compared to CUBLAS. And then the rest of that is just checking the correctness that the matrix is the result of our kernel is correct, because if our result isn't correct, performance doesn't matter. And so eventually, so as you see, again, in line 99, we call C.multiply add, which is matrix multiplication, and both parameters false, false means that both matrices A and B are non-transposed. And I have implemented myself 3 different algorithms for GEMM, where both input arguments are non-transposed. I will go through those kernels and show the optimizations that I was doing gradually to improve performance. But then once everyone understood that, you can actually go ahead and implement different cases where either A or B or both matrices are now transposed, and you'll just have to implement your own kernel. And then you can just provide, instead of false, false, you can provide true, false, false, true, or true, true. And this will be dispatched to your implemented kernel. And then you can measure your performance and see how well you're doing. Okay, this is just to explain what's going on inside main CPP, inside useBLA function, which drives this testing. So I'll go back to my presentation. And essentially, I explained this slide already. And now, so all the CUDA kernels are located in the blah_lib.cu. So if you see it at the bottom of this slide, there's a source file called blah_lib.cu, so which means that it contains CUDA code. And there are 3 different families of kernels. So one of them called GPU_GEMM_NN. This is the brute force implementation, which I call, and NN means that both matrices are non-transposed. Then more optimized version is called GPU_GEMM_SH. NN, where SH stands for optimization based on the use of shared memory. And then even more optimized version now is called GPU_GEMM_SH_reg. And this stands for even more optimized implementation, which uses shared memory and registers to improve the performance. And consequently, we'll be focusing on these three CUDA kernels to see which optimizations were done there. And then the goal will be to implement similar kernels, but for cases where one of the arguments is transposed. And those kernels already present in the blah-lib.cu, but they're empty. So the goal is to actually provide the implementation. Okay, I already described that. So just to remember, in the blah-lib, matrix AMN, so matrix with M rows and N columns. So the first index is row index, and the second index is a column index. And so the blah library employs column-wise storage. So when it allocates matrix in memory, in BLAS, it's standard to use column-wise storage of data, and that means that the elements are stored in the order of A00, A10, A20, and so on until the M dimension. Then the second index changes. So it's a column-wise storage. And consequently, in order to compute the linear offset of element jk in storage, then you need to multiply k by the number of rows, n, and add the offset of the row. So column number times number of rows plus row number. So this gives you the location of the element inside the matrix when you will be programming the GPU kernels. So M is the leading dimension extent in this case. And again, just to make sure that everyone has a clear definition what I mean by transposed cases. So the case which has implemented GPU kernels is the false-false case, where both A and B are non-transposed. And here is just CMN equals AMK times BKN, and the summation goes over K. So there is no summation sign here. It's implicit, but so it's always summed over index K. So when you do false true, then you implement AMK times BNK, where you see that the B is now transposed. When you do true false, then A is transposed, so you K and M are switched. And when you do true true, both A and B are transposed, so K and M are switched, and N and K are switched. And so we will need to provide implementation for those kernels. So again, as I mentioned, all this work should be done in blah_lib.cu. This is our source file, which contains CUDA GEMM kernels. So again, also I mentioned that. So the case which is implemented false-false has three different types of kernels, and they differ in the level of optimization. And so NN means both are non-transposed. Now NT means normal transposed. TN suffix means transposed normal, and TT suffix means transposed. So this is just to distinguish different cases where input arguments are transposed or not. All right, so before proceeding to the GEMM kernel, just I'll describe the matrix addition kernel first. So the matrix addition kernel, as all other kernels, all other GPU kernels, they are defined in the blah_lib.cu. So these are templated functions, but they're kind of trivial templates. So the template here is type T, and T can be either double or float. So for people who come more from C world, just then imagine that T is either float or double, and the rest should be straightforward. Then also the arrays, the pointers to the storage of matrix elements. For example, in this case, we are adding one matrix to another matrix, which translates to adding the storage of one matrix to another matrix. and we just provide pointers for our destination matrix and source matrix. So array 0 here is the destination matrix, the result, and array 1 here is the source matrix, the input. And as you see, so these pointers are marked with the restrict qualifier, which comes from CUDA programming model. And here, I mean, here is not very important, but I always put it in cases where we know that the pointers are non-aliased, so they don't overlap. And I always put this in the function interface to provide information to the compiler that these pointers, they don't point to the same storage, they don't overlap, and the compiler then, whenever it's appropriate, can do optimizations. And so this is the matrix addition is very simplistic. Essentially, we view the storage of matrix A and matrix B as just a linear array. And then we, so if you see at the bottom of the slide, this line represents this linear array where the matrix elements are stored in a column-wise order. And so this array has some size. And then we just take all the threads we have in the kernel. And we have grid_dim.x, this is the number of blocks in the kernel, and block_dim.x, this is the number of threads in the block. So the total number of threads is the grid_dim multiply block_dim. And so consequently, we let each thread to add its specific element of the input array to the output array. And the index of this element is simply the global number of the thread. And you see this, it's just a single for loop. And in the single for loop, the index is computed simply by evaluating the global thread index. And then moving this, because the array can be longer than, in general, the array can be longer than the total number of threads. We need to loop until we, excuse me, until we exhaust the full array. So we compute the first part using all threads, then proceed to the next part, and until it's over, then the addition is completed. Okay, I will skip the norm, because it's a bit specific here. But so let's proceed now to our main goal. So our main goal now is to consider the GPU general matrix multiplication kernel and see what kind of optimizations can be done to improve its performance. And so did you guys look around? So you ran the test, right? And so you want to tell me the numbers. If you see the performance there, it says for each type of algorithm, it says the performance of each algorithm. So the first one is the cuBLAS, and then brute force, shared memory, and shared memory plus registers. So what do you see the numbers there? Okay, so for cuBLAS, this is the highly optimized BLAS implementation by NVIDIA. It gives about 2 teraflop per second. Yeah, so the brute force algorithm gives. Yeah, that's what I'm. So the cuBLAS implementation gave 2 teraflop per second of performance. Then the brute force implementation of matrix multiplication kernel gave only 142 gigaflop per second, which is more than 10 times slower, right? So the next one has some optimizations, and what that gives. So the next one with optimizations based on shared memory gives 264 gigaflop per second, which is almost twice faster than brute force. And the last one gives. And the last one gives 580 gigaflop per second, which is still far from the cuBLAS performance, but it's not really our goal to actually achieve the performance of cuBLAS, because it involves lots of technical detail, and it's known how to do it. So our goal is kind of to learn some basic optimizations that can improve the performance, but we are not trying to achieve the performance equal to cuBLAS. But you can see that with each new optimization, the performance almost doubles. So, and that's we'll try to see why. So the first kernel from the blah underscore lib.cu is a brute force GEMM kernel, which is called GPU underscore GEMM underscore NN. So if you find that kernel in the source, you can just look directly in the kernel. And again, the template here is just T is either float or double. So it can support both single and double precision arithmetic, whichever you choose. So T is just single, T is just float or double. Then again, all the pointers to matrix storage. So dest here means destination. This is the matrix C storage, pointer to where matrix C is stored on GPU. Left here means the left input matrix is matrix A, pointer to its GPU storage, and B is the right matrix, is the second input matrix and the pointer to its GPU storage. So then here the brute force algorithm essentially takes matrix C, which has m rows and n columns, and then it splits, decomposes the matrix C into individual tiles of some row dimension and column dimension, and each tile is computed by a separate block of threads. So this is just the basic implementation of GEMM algorithm. And for example, in these first two lines in the function body, in the kernel body, we see that we just compute the position of the thread in the m dimension and position of the thread in the n dimension. I mean, the x and y dimension, right? So rows are the x dimension, columns are the y dimension. Excuse me. And so we just compute, each thread computes its own position in matrix C. And so obviously each thread belongs to some thread block. So I mean, each thread block computes its own tile of matrix C, and then inside that tile, each thread computes its own element. And that's how the parallelization is done here. And then you see that once each thread knows which element to compute, it simply loops over the k dimension and does the dot product and computes computes the specific element of matrix C according to definition of matrix multiplication. So CMN equals AMK times BKN and sum over K. So in this kernel, we also have a few things to discuss. So of course, we are not guaranteed that our matrix dimensions are multiples of the number of threads in each dimension of the block. So consequently, we always need to, in general, we need to check the boundaries that in cases where the thread element, I mean, the thread can actually go out of bounds of the matrix. So we always preclude these cases by putting this boundary check that to make sure that we don't exceed the matrix boundaries when it's not multiple of number of threads in each dimension. And then now each thread initializes the accumulator register. Here is just a float called TMP, and it assigns it to 0. And this is just the compiler puts this in a register, and it is private to each thread. And then each thread runs the loop over the k index, over the entire range of the k index. And then each thread finds the element, its element of the left matrix, matrix A. Then it finds the element of matrix, the right matrix, matrix B, and then it multiplies them and accumulates in its own accumulator stored in a register. And then once it ran the full summation over k, then it stores the result in the matrix C here. So that's where we upload the register to back to global memory. And then in general, if the number of blocks in each dimension if the user specifies that number of blocks which is less than the size of the matrix, then we need to then kind of transpose them, I mean, to move them, translate them to cover the full matrix, so we'll have a loop in general. But in this case, there is not really a loop here because the number of blocks in each dimension here is carefully chosen to cover exactly the full matrix. So these two increments here and corresponding while loops, they actually don't do any loops. They just have only one iteration. But in general, they're required. But again, so let's go back to the main part here, and where we load an element of the matrix A and an element of matrix B, and then multiply them and store an accumulator. So matrix A, called left, and matrix B, called right, they are stored in the global memory. And if you remember from John's explanation that access to global memory is extremely slow, even though it's super fast compared to like CPU memory. But given the amount of compute the GPU has, the access to the global memory is orders of magnitude slower than the number of floating point operations the GPU can do. And the other thing to notice here is that if you look at the left matrix, so the storage, the pointer left, the element there indexed in the square brackets, it has the minor component is MPOS, right? And then MPOS is a position, absolute position in the M dimension. And that position has the minor element coming from thread index X. And because of that, 32 consecutive threads in a warp, they load 32 consecutive elements from the storage pointed to by left. And consequently, the global memory bandwidth here will be good because we're coalescing the reads from this location. However, for the matrix right, we see that NPOS, which is the position in N dimension and Y dimension. So that part it's proportional to the thread index Y. And that means that when we read data from the storage pointed to by right, now the threads read from the memory non-consecutively. And consequently, this will drop the bandwidth. So the two obvious problems here is that read of the one argument is not coalesced. So reading the right argument, consecutive threads, they don't read the element from the same position. Sorry, from consecutive positions. And then we also, it's easy to see that the total number of global memory accesses, so each block performs block dim X times block dim Y and times the full range of K loads from global memory, and this is per block. And then if we multiply by the number of blocks, you'll see that the total number of loads from global memory is 2 times M times N times K, which actually exactly the same as number of floating point operations. So this is very bad because we know that the matrix multiplication, the size of the data is much smaller than the number of the floating point operations. But in this algorithm, the volume of data we load from global memory is the same as the number of floating point operations. Consequently, this kernel is global memory bandwidth bound. And we can never get any good performance out of this kernel. And that's why it performs so bad. Like more than order of magnitude slower than the optimized implementation. So what we can do about it? So the standard approach here is to deploy shared memory. So again, we have matrix C M by N, and each thread block computes its own tile. And as before, so the grid is two-dimensional and the block is two-dimensional. So the grid consists of grid of blocks in 2 dimensions, and each block consists of grid of threads in 2 dimensions. And so each block and each thread has two integers to point the coordinate of that block or thread. Because the matrix is 2-dimensional, so it's natural to map this problem to 2-dimensional blocks and threads. Then again, as before, the matrix M and C M by N, each thread block computes its own tile. And the tile size, as before here, the tile size here is 16 by 16. So it's a pretty small tile. So essentially, so we decompose the matrix C into tiles 16 by 16, and we give each tile to individual thread block, and the thread block has 16 by 16 threads. So each thread computes its own element of the tile. And so now what we can do is how to improve the performance of the brute force algorithm. So on the right side of the slide, we see that this tile of matrix C, for example, the tile which is assigned to thread block 0, 1. So this tile has dimensions block dim x times block dim y, which in this case is 16 by 16. So we have a 16 by 16 tile of matrix C. And then, in order to compute this tile, the thread block assigned that tile computes the summation over the full range of k. And this where we get this enormous amount of data loaded from the global memory. And so instead, we can introduce a shared memory buffer. And instead of every time we need an element of matrix A or matrix B, instead of going every time to global memory, we load some intermediate buffers in the shared memory with the tiles of matrix A and matrix B. And then we just do the multiplication of these two tiles by loading the data from these buffers from shared memory. And shared memory has much faster bandwidth than the global memory. So in this way, we want to make sure that since we have some data reuse in this algorithm, so we want to maximize this data reuse, that the data is coming from the fast memory instead of the slow memory. And so how this is implemented is the following way. So this could be a bit small font, but if you for some reason don't see what's on the slide, on the left side, the source code, you can always open the source of this kernel, and the kernel is called GPU_GEM_SH_NN. So this is the shared memory optimization, and you can just directly look at the source code. They're the same. And so in this way, first of all, you may notice that now our template also provides 3 constants: N capital, M capital, and K capital. So these are the tile dimensions now. And N and M, in this case, equal to 16 by 16. So the M capital, N capital is 16 by 16. So our C tile is 16 by 16. And each tile is assigned to a thread block. But we also now tile the K dimension. And now our K dimension also consists of segments, and each segment has size K capital. So this is now the third argument, now the tile of the K segment. So, and also the next thing to notice that we now declare the 2 shared memory buffers. So we use the __shared __ qualifier to tell the compiler that arrays LBuff and RBuff, so they are now stored in the shared memory of the streaming multiprocessor. And so the shared memory, so all the variables and arrays with the shared qualifier, they have the scope within each thread block. So they're only visible within each thread block. So each thread block has its own private scope, and the shared is only visible inside the thread block. But all threads in the thread block can access the data. And so we declare two buffers, LBuff and RBuff, and we give the dimensions correspondingly K capital, M capital, and A capital, N capital, K capital. And this is just defines, if you look on the right-hand side, the LBuff just loads that stripe of matrix A. So there are three stripes there. So LBuff just loads like any of those stripes. And you have M dimension is the number of rows in the tile, and now K capital is the dimension is the number of columns in this stripe of the matrix A. The same applies to matrix B now. You see that delta K, so delta K is essentially the K capital. And so now we also load the stripe of matrix B in the RBuff. And the dimensions are number of rows is N capital, which is 16, and number of, number of columns is N, and number of rows is K. And in this case, I believe K is 64. So the K capital is 64. So we load, in this algorithm, we load a tile of matrix A of dimension 16 by 64, and a tile of matrix B of dimension 64 by 16. And then we multiply this and sum over the K dimension, which has 64 elements. And then the result is 16 by 16 tile of matrix C, which is what the thread block is computing. And so if we proceed to the algorithm, you'll see now again that you have two loops over Y and X dimension, which again you can ignore, because this loop's only required when you don't when the dimensions of the matrix exceed the dimensions of your grid of CUDA threads. So you can just ignore those loops. And as before, you see that each thread computes a specific element in the tile of C, and we initialize the accumulator to 0. Each thread initializes the accumulator to 0. And then now the important part is the loop over K. And you see that the third for loop over index K is going through it's going through the full range of index K. But now it's going strided. So it's going K capital elements at a time. So this is the loop over the stripes that you can see on the right-hand side, right? And so then once we chose the particular two stripes from matrix A and matrix B, which we want to multiply, we load those stripes into shared memory. And that's what those two blocks of code in red at the bottom of the slide do. So we read the left matrix. We read the tile from the left matrix into the LBuff, and we read the tile, that stripe of matrix B, into the RBuff. And now notice that in both cases, when we read data from left matrix and from the right matrix, in both cases now the minor component in the offset of the element that we read, it's always proportional to the X, thread index X. So the minor component here is thread index X, which means that in both cases, 32 consecutive threads in a warp, they load 32 consecutive elements from the global memory, which means that we have a good coalesced access to the global memory, and we maximize the global memory bandwidth. And then, so in this way, we load the shared memory buffers LBuff and RBuff. And now these two buffers, they contain the stripe of matrix A, and this tile, and the tile of matrix B. And then importantly, we now need to synchronize, so sync threads, perform synchronization of the threads in the thread block, inside the thread block. So it's essentially a barrier. Because we need synchronization here because we will be using these buffers that we are loading now, we will be using them in the next part of the code. So consequently, to make sure that they are fully loaded, we need to synchronize the threads. And then we proceed to computation. And in this loop here, first of all, let's focus on the parts in red. And we just simply take these two tiles that we loaded in the shared memory buffers. And we simply then run a loop over the k dimension of the tile. And we just simply multiplying elements from lbuff times elements from rbuff, which are now loaded from shared memory. And we just, as before, accumulating the result in the TMP variable. And why do you see two of them here is that in most cases, we know that the k dimension of the tile is just this k capital, except maybe the last tile, which is not necessarily aligned to the number of so the total dimension k of the matrix is not necessarily a multiple of the k tile dimension. But in all but one case, we know that this loop has a predefined known number of iterations during compile time. And in this case, it's always often profitable to insert pragma unroll right in front of that loop, just to tell the compiler that it can safely take that loop. And instead of just doing the loop, actually, it can just take each iteration and execute it just as a separate statement. And in this way, the loop will be unrolled. And instead of just checking the condition for the loop when the loop is over, since we know a number of iterations, we just put instead the same number of these instructions as just a list of instructions. And this often helps to improve the performance. And so we simply check if we know the number of loop iterations, then we unroll the loop. But what the loop does, the loop just multiplies two tiles, tile of A times tile of B, and accumulates the result in the TMP variable, which is the element assigned to each particular thread. So, and if you now analyze, if you look now on the right-hand side of the slide, and if we now analyze how much data is loaded from the global memory, then you'll see a reduction in the number of data loaded from global memory per block. And you'll see that each block loads block dimension y plus block dimension x times the full k range. And you'll essentially see, is it on the next slide? Yeah. So you essentially see now on the top right corner of the slide that the number of global loads per kernel will be 2 times m times n times k. These are the matrix dimensions. But now it will be divided by the size of the m tile when m equals n, for example. Like we have 16 by 16 tile, so we'll have 16 times less loads from global memory performed, and this is good. So we reduce the number of loads from global memory, and it's always profitable for performance to reduce the number of loads and stores from global memory. And consequently, this is one of the factors that improves the performance. So we now have much better data reuse. So instead of just loading every time we need a new element of matrix A or B, instead of every time going to global memory, now we preload some buffer, and then we do most of the reads from the shared memory instead of global memory. So in this way, we reduce the number of global memory accesses, and we get the better performance, of course. But it's still, as you saw, performance is still 260. So it was like nine times worse than the optimized cuBLAS, right? So obviously we're not even close. And there are two problems with this kernel. And so if you go back, if I go back in the slides, you see that now the kernel body now has these two alternating phases. So in the first phase, all threads in the block, they load the buffers. Then there is a barrier. And then in the second phase, all threads in the block do the compute. And there is again a barrier. And this kind of introduces an excessive synchronization in the kernel execution. And the strategy to optimize this is to use double buffering and pipelining of the loading of data from global memory and computation. So this is one of the reasons which we'll actually not touch. So I'll just mention it, but there is no kernel which does that optimization. But the other thing is that when the compute is performed, all the threads, they still, even though shared memory is much faster than the global memory, but there are lots of loads done from the shared memory, and shared memory access is not free also. And when accessing the shared memory, it's important. The pattern of accessing the shared memory is important because of the so-called band conflicts, and consequently. We need to be very careful also how we load data from shared memory. And if you want, like later, you can actually simply exchange the dimensions of LBUF or RBUF instead of just this first, this second. Now do that second, this first. And then you will see that performance can drop like twice. So it's important to, I mean, here the pattern is optimized. But in general, this can be a problem also. So the accesses to shared memory are not free. They're much faster than the global memory, but they're not free. So they have cost. And the other thing that finally, again, we may notice that each thread computes its own element of the C tile. And for that, it runs the loop over the entire K range of the matrix. So essentially, each thread computes one element, and it loads K, where K is dimension of the matrix, K elements from matrix A. It loads K elements from matrix B. They're loaded from the shared memory, but the number of operations here is K, and the number of data loaded by each thread is 2K. So essentially, we do more loads than the floating point operations. So again, even though the shared memory is very fast, compute is still faster. And here we cannot satisfy our compute capability of our streaming multiprocessors because we load more data than we do compute. So we always need to do more compute than loading data. So all the optimizations in GPU kernels are focused on reducing the number of memory accesses and increasing the ratio of number of compute to number of memory accesses. So how we can do, what else we can do here to actually fix this problem? So we can try to use, shared memory is already very close. So it's inside the streaming multiprocessor. But we know that registers available for each thread, the access to registers is even faster than shared memory. So we may now try to actually exploit the registers, kind of the next level of memory hierarchy. So we started from global memory and go directly to compute. Now we introduced shared memory, so we go global memory to shared memory, and then do compute. And now we can do another level, introduce another level of memory hierarchy and do global memory to shared memory to registers, and then do compute. I mean, compute is always done from registers, but we can now play with the registers to see if we can minimize the number of accesses to shared memory. So this is very similar to what we did before, but just now we are minimizing the number of accesses to shared memory. Again, so the next kernel, so again, the algorithm is very similar. So each matrix C M by N, it's decomposed into non-overlapping tiles. Each tile has, okay, the next slide. Each tile has dimension M capital by N capital. And in this case, M is 64 and N capital is 64 also. So before we had 16 by 16 tile of C. Now we have 64 by 64 tile of C. So now each thread block computes, instead of 16 by 16 tile of C, now each thread block computes 64 by 64 tile of C. And does very similar things again. So it chunks the dimension K into the segments, where each segment now is 16. So now we have a tile of C is 64 by 64, and the K segment is 16. Consequently, we load tile 64 by 16 from matrix A into shared memory. Then we load tile 16 by 64 of matrix B from shared memory. And then we multiply those tiles together as before and produce a tile of matrix C, which now has dimension 64 by 64. However, the problem is now that, I mean, this is not a problem, but we need to note now that before we had tile of C dimension 16 by 16, and we also had 16 by 16 threads within the thread block computing that tile, which means that each thread was computing precisely one element, exactly one element. And that's where the problem was, that the number of compute operations performed by each thread was the same order as the number of loads from shared memory, which is bad. So now we see that 64 by 64 tile, we now compute this tile still using 16 by 16 threads. So our thread block is still the same, it's 16 by 16. But the tile computed by this thread block is 64 by 64, which means that each thread now computes 4 by 4 sub-tile of that tile. So before it was a single element, now this is 16 elements. So each thread computes 16 elements of the tile assigned to the thread block. And that's how we increase the compute intensity. And now we need to notice the other thing is that, so if you look at the tile of matrix C on the slide, you see this red circles. These are the 16 specific elements computed by specific thread. So there is a thread which computes those 16 elements. And you should notice that those 16 elements, they are not adjacent to each other. So you see that they are actually strided. And why? Because, so you see that the tile of matrix C now, which has dimension 64 by 64, now is split into 16 subtiles. So because the dimension of the tile is 64 and number of threads is 16 in each dimension, then we have 4 segments in each dimension. And then we have 16 subtiles inside the tile of C. And then within each subtile, each thread computes its own specific element. And then we just stride to each subtile. And then, for example, thread number 42 computes element number 42 in that subtile. And then in each subtile, it computes element number 42. But those elements, they're now located in different subtiles. So the thread computes elements from different subtiles. And each thread computes 16 of those elements. But now the cool thing about it is that to compute this 16 by 16 small matrix, sorry, 4 by 4. So to compute the 16 elements of this now 4 by 4 matrix, it only needs to load 4 elements from matrix A and 4 corresponding elements from matrix B. And this is done for each K. So given a specific value of K, each thread inside the thread block needs to load 4 elements from A, 4 elements from B, and then it can compute 16 elements of its contribution to C. So now we see that we only load 8 elements and we compute 16 elements. So now our ratio compute to the data, to the memory transactions raised like 4 times, right? And then, so the rest of the algorithm is just for each k, we load 4 elements from shared memory of A, 4 elements from shared memory from B, that's each thread does. And then it performs the outer product of these two, and it computes 16 elements of C. And those 16 elements now are stored in the registers. And those 4 elements that we load, they're also stored in registers. And the algorithm looks like this. So, and then we just loop over k, which is just illustrated here. Next k, next k. I mean, over the tiles of k. So first tile of k, second tile of k, third tile of k, and so on. At the end, we have computed the full contribution over k. So this is now how the kernel looks like. Again, it has the same template, where just the type is either float or double, and you have these parameters now n, m, k, which specify the tile dimensions. And now n and m are 64 by 64, and k is 16 now here. And the kernel is called GPU GEMM sh underscore reg underscore nn, because it's now using registers to optimize the shared memory loads. And as before, you see that it's still using the same buffers, lbuff and rbuff, the same dimensions, everything's the same. And those, again, 2 loops you can ignore, because they just, for general case, when the matrix dimensions are larger than the dimensions of the grid, of the kernel grid. But then, so what we do now, before, if you remember, we had a single variable called TMP, and then each thread initializes this single variable TMP, which will accumulate the result of that thread computing its own single element of tile C. Now each thread computes 16 elements of tile C, 4 by 4. So now we put a small array called dreg 4 by 4 into registers. And the way it's done is that to make sure that the array is in the registers, which is non-trivial, by the way, first of all, the array dimensions should be compile time known. So here are just numbers, 4 by 4. And second, whenever we access this array in the kernel, the address, I mean, every time we access that array, the indices must be, the indexing must be understandable to compiler. So we cannot do some kind of indirect indexing, and then this will actually cause a serious problem, because that dreg array will be moved to the local memory, and local memory is the global memory, and that will kill the performance completely. So to make sure that the small array is in the registers, it needs to be small, its dimensions needs to be compile time known, and whenever we index that array, it should be clear from the code which element we access to the compiler. So now we see that we put dreg 4 by 4 array in registers. Then we put rreg and lreg, just small arrays of 4 elements each in registers, and we initialize them to 0. And then, so the next part of the kernel is before. We just simply load the tile of A. So we loop over the k dimension with the segments. So k capital, right? So we have the stripes of k dimension. And we loop over that k dimension with the segments of tile xk. And then for each segment, we load tile of A, which is m capital by k capital, and tile of B, which is k capital by n capital as before. Just the way we load it now is a bit different, but I don't think we need to probably go in that detail. Right. So, so you see that there is a new loop now. So when we load tile of A and we load tile of B from global memory into shared memory, now we have an additional loop because now dimension M of the tile and dimension N of the tile, they now exceed the block dimensions. So the thread block is 16 by 16, but the tile is 64 by 64. So consequently, to load dimension M, which is 64, extent of 64, we need to do the 4 times 16 plus 16 plus 16 plus 16. And that's what that loop is. But we still have careless memory accesses. And so we just load 2 tiles as before, tile of A and tile of B into shared memory. Synchronized threads at the end, if you see, again, because we have this loading phase and then computing phase. And now the computing phase, what it does, so there are, again, 2 cases here. And so this is just an if block. And so the first part of the if block is just checking if we know the number of, if the dimension of the K segment is compile time known. So in this way, so we know the number of iterations in the K loop, and then we can use additional pragma unroll to unroll that loop over K, over the tile of K. But that's irrelevant. I mean, you can ignore that. That's not important. So what's important now is the next 2 loops. So the next loop now, you see, so those lines which have in red, bold red. So now, since we have a tile of A and tile of B in shared memory, now we load 4 elements of A tile from RBUF to RReg. So that's first loop. Then we load 4 elements of the B tile from LBUF shared memory into registers LReg. And then we do compute loop, which performs 4 by 4, 16 computations. And it does the outer product of these two vectors, right? So 4-dimensional vector loaded from tile A from shared memory and 4-dimensional vector loaded from tile B from shared memory. And then it performs 16 floating point operations, actually 32, because it does multiplies and additions. And so now we see that the number of floating point operations performed by each thread now noticeably exceeds the number of loads from shared memory. And so we now maximize the arithmetic intensity. And this always results in better performance. And that's why you see that the performance of this kernel is like twice faster than the previous version. Right, so just performance 4 by 4 outer product. And again, at the end, as before, once these 16 elements are computed by each thread, then each thread block finished computation of its tile 64 by 64, and then it just simply uploads the tile of 64 by 64 into the global memory as before. And you can see here the upload is done directly from registers. And you need to be careful here. So the difficult part here is to provide the correct indexing in the matrix C, which is this pointer dest, to make sure that those 16 elements are placed in the right positions in the matrix C. Okay, so this concludes the explanation of what kind of basic optimization one can do to improve the kernel performance. And improving the kernel performance means minimizing memory accesses from slow memory and maximizing the number of floating point operations performed per each memory access. And these 2 things increase the performance. And so now, so these 3 kernels that I just described, they can be found in the blah_lib.cu source file, and they call GPU GEMM NN, GPU GEMM SH NN, GPU GEMM SH reg NN. So they implement these 3 different algorithms with different level of optimization for the case when both A and B matrices are non-transposed. Now you have like empty placeholders in the blah_lib.cu source file, if you look at it, and you'll find so this empty placeholders, just prototypes of these kernels for different cases where one of the matrix A or B or both of them are transposed. And this like suffixes nt, tn, and tt. So they just designate whether the first A argument is normal and B is transposed, or A is transposed, B is normal, or A is transposed and B is transposed. And the exercise is now to fill in and populate those empty kernels with the implementation, which would now perform the matrix multiplication for these cases. And for example, you probably don't want to implement all three of them and then try. So the easiest way probably is just to, for example, take the brute force algorithm, which is the simplest one, and just implement a different case where one of the matrices is transposed. So once you've done that, you can just go back into the main CPP and find the block which corresponds to the brute force algorithm, and replace one of the false in the multiply add call with the true, corresponding to which case you implemented. And then, so you also do not want other cases to run. I mean, other algorithms to run, because if you start doing matrix multiplication with one of the argument transposed, then all the calls to the GEMM kernels should also be so. Consequently, what you want to do is that you'll see there that at the beginning, let me show you here. So all you need to do is this. So once you implemented your kernel for specific algorithm, either brute force, which would be a good start, or shared memory, or register-based, for the specific case where one of the arguments is transposed, for example, then you pick, for example, here you say test brute force true, and you don't want to focus on other. So you don't want to run others. You just put false here. So you don't need to run them now. So you only test in the brute force algorithm for a new case, and then all you need to do is just you go to the reference case, which is BLAS call, and then you specify, for example, the first argument now is transposed. So you put true here, line 82. So this will run a CUBLAS kernel, a highly optimized kernel from NVIDIA for GEMM. And it will call this kernel now where the first argument now is, the first matrix is now transposed because you put true here. And this will give you still similar good performance and the correct result. And now you go down to your brute force block where you test in your brute force algorithm, and you do the same here. So now you want to, in line 99, you want to run matrix multiplication where the first matrix operand is transposed. And once you implemented the kernel and you did these adjustments in the main CPP tester, and then you'll see if it runs, and for example, it can report that, first of all, your kernel may crash, and then you will notice that. Second, the kernel may run to completion, but here's a check where it will test whether your matrix C is correct or not. If your matrix is computed but is incorrect, you'll see that it will report that. Then finally, if the matrix C is correct and it corresponds to the CUBLAS matrix C to some precision, then it will report what the performance is. So all you need to do here is that pick a case you want to implement, like specific algorithm and specific case of matrix transposition. Find that placeholder kernel prototype in the blah_lib.cu source file, implement that kernel, go to the main CPP, choose which algorithm you're testing here in lines 28, 29, 30. So you're testing brute force, you're not testing shared, you're not testing register-based. And then go to CUBLAS reference calculation and adjust the transposition parameters to what you implemented. And then go to your implementation call and adjust the transposition parameter parameters to what you have implemented to match the kublas. And run. I mean, rebuild and run. So at this point, I'll be just waiting for questions. If we have any time left, I don't know. Do we? Oh, cool. So yeah, I will just be waiting for questions, and I'll let you play with it. If you want. Okay,
so,
cool.
Dmitry, you're done presenting, correct?
I believe so. I mean, I can go back to any part if there is some confusion or not enough understanding of some part that I described. I can go back and explain more, but other than that, I'm done.
Okay, why don't we hang for a little bit, let people take a break and see if there are any questions while they work through the exercises.
So I might just ask a question. Is anyone working on the exercises?
Several nodding heads here at NCSA.
Was it yes? Oh, cool. Cool. Great. Okay, that's good then. Yeah. Right. Well, I mean, it looks a bit complicated because you only had 15 minutes to look at it. so in fact, it's very trivial. Right. So what BLA-libQ includes is just some basic like utilities for converting between different types. Then it includes the dispatching function, because we are whenever we are writing a heterogeneous application, we can just say, I want to do only GPU computing. So once it becomes heterogeneous, now it's always a good idea to provide a unified interface where you can dispatch your call to either CPU or GPU based on your preference, and make the interface hardware agnostic, so such that the interface does not explicitly have any detail of the hardware. And consequently, you normally write a dispatching function. For example, allocate body, right? So this function allocates the storage for the matrix. And so instead of writing allocate body underscore GPU or allocate body underscore host, you just write in one function, allocate body. And then you tell that function that which is a GPU or a host, and then underneath it will allocate the body or the storage of the matrix on the device that you want. And consequently, this is your code becomes, your high-level code becomes hardware agnostic. So you never care about all the slug details here. And consequently, the same in that blah_lib.q file. So there are these dispatching functions which multiply, add, compute norm, and matrix addition, right? And all they do, they just take your arguments and see which device you want to multiply. Perform the operation on, and then there is a simple switch. We say, okay, so here, the user wants to perform this on CPU, call CPU kernel of function. Then the user wants to perform computation on GPU, okay, call GPU kernel, or maybe do some additional preparation for that. And so in this way, it's very simplistic file, so there's nothing hard there. And also, again, the focus of this is not to learn the whole code structure of the BLA library. So it's all like bookkeeping. So the focus is only, there are specific kernels there which don't have implementation. So you only need to find the function that you want to implement, the kernel that you want to implement, and provide the implementation, and then rebuild and run. So you don't need to understand what's going on in the rest of the code. So just once you provided the correct implementation for the kernel, then it will automatically work as a part of the library. Yeah. Right. So what I normally do again, yeah, right. So okay, sorry, I understand the question. Yeah. So what I normally do, yeah. So again, so I have the interface exposed to the user. I normally make hardware agnostic, so it does not carry any information on the whether it's GPU or CPU or whatever. And then you just provide the arguments which can dynamically or statically during runtime, or sorry, during compile time, actually select which device you want. But that requires then writing this kind of a dispatch part of the code, which will accept your hardware agnostic calls, and then to dispatch them to hardware specific implementation. And so you interface is hardware agnostic, and then dispatcher will dispatches the computation or memory transfers or allocations to the implementation for specific device you want. And so yeah, so in this way, yeah, and then of course for the GPU implementation, you'll have a CUDA file. For the, I don't know, Xeon Phi implementation, you will have some other file which performs same kernels on Xeon Phi, right? I mean, as long as you use the hardware-specific optimized programming model like CUDA. If you have like OpenACC implementation, then you only need to vary like the parameters of some parameters of your OpenACC code, but you don't rewrite the source code. So the source code stays the same, ideally, which probably never works. But if you really want to provide highly optimized implementation, then you need to follow this dispatch route, where the implementation is selected from the hardware optimized code. Yeah. Question?
From Leonardo, could you explain again just the part of the use of registers in algorithm 2? And in the case if you use too many registers, would it be better to use shared memory for the tile results?
Can you say the last part again?
Use too many registers, would it be better if you used shared memory for the tile results?
That's a good question. Yeah, very good question. So, yeah, as John mentioned before, each streaming multiprocessor inside the GPU card, it has 64, I mean, it's not fixed, but normally it's like 64 K of registers. So 65, 536 registers. And it has, for example, 48 kilobyte of shared memory, right? And then the amount of shared memory per kernel and the amount of registers you request per kernel define how many blocks can be executed, how many blocks can be active on each SM at each point of time. And I mean, this is called occupancy. And you always want to maximize occupancy. But for example, with the algorithm 2, it's actually hitting hard on resources. So first of all, it's using quite a bit of shared memory, right? So it's like 64 by 16, so it's like and 2 buffers. So it's 8 kilobyte. So every block, every CUDA block requires 8 kilobyte of shared memory. And so each thread, whenever you actually build the code, there is an option specified there which actually prints how many registers each kernel uses. If you do the make, you will see how many registers each kernel is using. And I believe it was something like 65 on Kepler. So each thread is using 65 registers. And consequently, you cannot run more than so if your thread block is 256 threads, then you can even run even 4 blocks, because you will run out of No, actually 4 blocks, yeah. So at most you will run 4 blocks. Right. So you can run 4 blocks, 4 thread blocks per SM. But if you now decide to, why don't I increase the number of registers? And because the larger this, if you see the slide now, the larger this red subtile is, so this number of elements computed by each thread in registers, the better the performance should be. But if you now try to increase it twice, then you will only, so you will, each thread will require so many registers that you will only be able to run only 1 block per streaming multiprocessor. And this will actually kill your performance. So instead of just seeing the improvement, you will see that your performance degraded enormously. And consequently, yeah, it's always, you always need to count the number of registers used per each block and the amount of shared memory used per each block, and to consult with the specification of your GPU device to see how many CUDA blocks you can run simultaneously on each SM, and to maximize the occupancy of CUDA blocks. So consequently, for example, like for this case, for algorithm 2, it's actually, since you cannot run more CUDA blocks per SM because you're already kind of getting high on register usage and shared memory usage. So now this like barrier that I mentioned, this like sync threads. So when you load the data in shared memory and you call sync threads, it's a barrier. So all threads synchronize. And then you do compute and you again call sync threads at the end. So now this is kind of a two-phase execution where you have a phase of loading the data and phase of computing the data, and they alternate. So now actually this becomes a killer. And then what the next optimization, what you would do here is just to introduce this kind of a double buffering strategy where you would allow threads load the data while they're doing compute. And so kind of to interleave now the data load and computation, but because you can load now the next tile while you're computing the previous tile. And that would further improve your performance. But yeah, so it's very important to understand how much resource registers and shared memory each block consumes, and consequently to make sure that you can have at least 2, but this is just the bare minimum, but better like 4 or more blocks simultaneously resident on each SM. Hope this answers the question. Great. No more questions? That's...
Leonardo says thank you.
Sure. Then I hope we'll get soon, in 5 minutes, we'll get the kernel implementation. And we can see the performance. Yeah.
So I got one implementation of the transpose working, and I actually have a worse performance than the. So I did the naive implementation.
So which one, the brute force or?
The brute force, yes.
And you did the TN case or NT?
The TN case.
Okay.
So before, I think we had about 140 gigaflops.
Right.
And now I have 88.
Right, and you know why, right?
I think it's because of the way the memory is accessed, since now we have the ordering of the indices swapped.
Right.
Is that correct?
Right. So if you remember, so in the brute force case, you have left times right, so matrix A times matrix B, and both are loaded from global memory. And in the regular case, then the left matrix, 32 consecutive threads in the warp were loading 32 consecutive elements from the memory. So this is coalescence. So that this guarantees good bandwidth. But the write argument was loading actually, yeah, so there was some stride there. So like the first 16 threads load one element, then the next 16 threads load strided element. So it has not optimal global memory access pattern. So now when you introduce Tn, now you transpose the left argument, right? The one which was actually good, and now they're both bad, yeah, right? So that's exactly the case, yeah, when you see. But now, if you're curious, if you put NT, you should see better performance, because now the write will be transposed and you'll see the improvement. Do you have any time? I don't see any time anywhere here. Okay. Oh, so we have plenty of time. Great. So just to broadcast the first result, so we got a successful implementation of GEMM brute force for Tn case, transposed normal. And as expected, the performance dropped. But at least, so now the BLA library was extended by a new implementation, and now it has one more feature, which is great. So if you have any other success stories, please share. One success, or just share. How many people in total do we have here? Oh, there is no such statistics. Only 300 people. 300. Oh, 300. Wow, a lot. A lot of people. That's good. Oh, so only 30% occupancy. Let's see. I think all the difficulty here mostly stems from the necessity of keeping the indexing correct, to making sure that the thread is indexing the correct element it's supposed to index. And yeah, I think that's probably the hardest part here.
Thank you for your presentation.
Sure.